And now we are ready to see this chart, and this is how it looks like. And we already talked about the upper part, the function of the reagent, and this is the substrate structure, primary, secondary, tertiary. We have talked about this in the introduction of alkyl halides, basically depending on number of beta substituents, right? And so we combine this substrate type, primary, secondary, and tertiary, with the reagent category to predict the mechanism. So we have 4 reagent categories that exclusively function as base, can function as nucleophile and only nucleophile, and just weak nucleophile and weak base. And the reaction mechanisms to consider are SN1, E1, SN2, and E2. And this outcome here, this whole chart is based on steric hindrance of substrate. So tertiary substrates are more sterically hindered than primary counterparts, stability of carbocation for unimolecular reactions, and reactivity of nucleophile or base. And as you can see, if we just analyze this in general, we can see that tertiary substrates here, they usually favor SN1 and E1 reactions, or E2 if you use strong base. And primary substitutes, they usually favor SN2, and if you use bulky base, they favor E2. Secondary substrates, actually all mechanisms are possible, all bimolecular mechanisms possible, depending on reagent and conditions. So the goal here is not to memorize this table, but to understand trends. So now I'm going to explain this by first taking a look at first 2 columns, leftmost 2 columns, basically strong bases. Then we will explore the rightmost 2 columns, weak base. First, we talk about this strong base and poor nucleophile like DBN or DBU. That promotes E2 reaction only, regardless of being primary and secondary or tertiary. So I'm talking about this part. They are strong base. So both of them are strong bases, but this is like nucleophile, so we don't expect any SN2 because they are poor nucleophile, right? And we also don't expect SN1 and E1 because they are strong base. There would not be any carbocation formation. Because they are strong base, they would just extract proton and try to make elimination reaction. They would not wait for carbocation to be formed. And carbocation would not be stabilized under those conditions. And in the second case where you have strong base and strong nucleophile, so for primary substitute, you can actually gonna form both E2 and SN2, but SN2 is gonna dominate because you will have this fast backside attack, right? Because you have primary substrate and your reagent is a strong nucleophile, apart from being strong base. So you will expect this fast backside attack. As you can see here, you are using first degree substrate like a primary, and you are using sodium OH, which is strong base and strong nucleophile at the same time. You are forming E2 and SN2 at the same time, but your major product will be SN2. First, because you have your SN2 is gonna form from fast backside attack. I'm specifically mentioning backside because that's the stereochemistry of SN2 reactions. You will form E2 reaction as well, but it's gonna be minor. And there's also second reason why this is minor, because if you are having primary substrate, then you can have monosubstitute alkene. And monosubstitute alkene is generally not very stable, right? This is monosubstitute. In compared to disubstitute, tri or tetrasubstitute, this is not very stable. So you don't have a lot of drive to have E2 pathway and to make this alkene. So that's why when you have strong base and strong nucleophile with primary substrate, you will form mainly SN2. So as you can see, SN2 have this larger space here in this table. So that means SN2 is a major product. But when you use secondary substrate, because of steric hindrance, your E2 pathway dominates because you have some steric hindrance here. It's going to be very harder for SN2 reaction to proceed. So your SN2 is going to be minor. And lastly, tertiary substrate, you have no chance for SN2 because it's very difficult. If you remember, when we have this rate comparison, it was very negligible, this rate for SN2 reaction. So you have no chance for SN2. And then you only form E2 reaction. And as you can see, E2 product is also disubstitute. So it's quite stable in comparison to monosubstitute. So that's why you have E2 as your only product. But you have this specific case. Usually this elimination dominates here in the case of secondary and tertiary substrate. And in the case of primary, SN2 dominates. But there is a special case where you use a bulky base. And bulky base is just, yes, it is strong base. It can also be a strong nucleophile, but it's bulky. So you would not expect this SN2 product a lot. But usually, just from talking from experience, whenever you see this potassium tetbutyl oxide, you will exclusively form E2 products most of the time, because otherwise why would you use this to form this, right? So I would use Williamson ether synthesis. We will talk about that when we learn alcohols or ethers. I would use this part as my nucleophile, and I would use this part as my electrophile, alkyl halide, so that I can make this reaction and to form this product. It's always good to deprotonate OH. That's actually Williamson ether synthesis. You deprotonate OH first, make alkoxide like O-, and then promotes that SN2. So in this case, this is special because you are using, even though this is primary substrate, and you would expect primary substrate to have E2 and SN2 at the same time, and SN2 being dominating, because you are using strong base and strong nucleophile. But because this is bulky base, you will have E2 favored. So this is useful only when you want elimination on a primary substrate. So whenever you have a primary substrate and you want to go exclusive, I mean not exclusively, but you want to go mainly with E2 reaction to have elimination product, then you would use bulky base. So the general trend here is that if you have strong base, you will have E2 domination. You see everywhere is E2. SN2 competes only when steric allows. For example, in first case and second case, you might have some SN2 because the stirring hindrance is not of a big issue, especially in the primary substrate case. And tertiary substrate, there is no way for you to form SN2, and there is no any exception. Next, we are focusing on the right hand side of this table, and here both of them are weak bases. And because you have weak bases, you will have slow E2 process, almost no E2 process, right? Because it's going to be extremely slow with weak bases. And because they are also weak nucleophile, you don't expect SN2 a lot. So this is basically a zone for unimolecular reaction, SN1 and E1. And product preference between SN1 and E1 depends on alkene substitution stability. Tetra is more stable than 3 substitute, which is in turn more stable than disubstitute and monosubstitute, right? And if you are forming more stable alkene, highly substitute alkene, then obviously your E1 is going to be preferred over SN1 for the tertiary case. So when you have SN1 and E1 together, the product preference depends on how stable the alkene is. If you are forming alkene, more stable, highly substitute alkene, your E1 is going to be preferred. So in general, your substitution is predominant here. You have only one E1 here, as you can see, for tertiary substitute and for weak base, right? And other than that, they are mainly substitution. So when you have strong nucleophile but weak base, obviously your SN2 is gonna predominate because it's fast and clean, right? Primary and secondary, it doesn't act as a base because it's weak base, right? I'm talking about iodine minus, bromine minus, cyanide minus. We will talk about cyanide in detail, but these are those categories where you have strong nucleophile and weak base. And for primary, it's fast and clean, right? SN2 reaction. For secondary, it's gonna be mostly SN2. There's actually some controversy here. People debate for secondary case, is it gonna be SN1 or SN2? But it's actually mostly SN2 because your secondary carbocation, if you form SN1 reaction, your secondary carbocation is gonna be not very stable. But when you have tertiary substrate like this, obviously, because it's weak base, right? You are not gonna form any elimination here, E2 reaction. So you will make this positive charge, and this is very stable. And then you will form SN1, and can technically form E1 and SN1 because we said that this is unimolecular reaction, and the first step, loss of leaving group and formation of carbocation, is the common step. But because you are having weak base, you are eliminating E1 here, and you are forming SN1. And obviously you cannot have SN2 here in the tertiary because it's blocked by sterics. And in the case of weak nucleophile and weak base, for primary and secondary, you don't have any reaction. And if you have any primary or secondary substrate, you will form a primary carbocation, which is extremely unstable, and secondary carbocation, which is also unstable. So you eliminate all E1 and SN1, basically unimolecular pathways. You are left with SN2 and E2. Because it's weak base, you don't expect E2 to happen. Because it's weak nucleophile, you also don't expect SN2 to happen. So the only case where you have reasonable reaction is SN1 and E1 pathway that is on third degree alkyl halide, because you have very stable carbocation and you can form E1 and SN1. Again, the rates are not going to be high because you have weak base and weak nucleophile, but still, these are the only pathways that you should expect. And this is an example for tertiary substrate. So you have a tertiary substrate, you have H2O, and H2O is a weak base and weak nucleophile. So you will form E1 and SN1, but because your E1 products are tri and tetra substitute, for example, here this is D substitute, but usually whenever you have tri or tetra substitute alkene as your E1 product, your E1 is going to be major. E1 is going to dominate. But if you don't form highly substitute alkene like monosubstitute or disubstitute alkene, then your SN1 is going to be. So usually these reactions are quite slow. That's why you often require heat. So whenever you see heat, that usually means you have this weak base and weak nucleophile. So you need to have some kind of energy in order to make sure that this reaction goes to some extent. And as I said, when you use weak nucleophile and weak bases, you don't have any SN2 or O2, like this part. I'm talking about this part, the X part. But there's one exception. This is allylic and benzylic. Because we already learned that even if you have primary carbocation, but if it is allylic position, then it's actually quite stable. So you can actually have some SN2 and E2 going here if you have allylic or benzylic. And benzylic is this one. For example, when you have a phenyl next to a positive charge, so you can have some chance for that positive charge to be delocalized over this benzene ring. So in the case of allylic and benzylic primary alkyl halides, you can form these allylic and benzylic carbocations, and they are quite stable. So this region, you can expect some kind of SN1 or E1 reactions because we are talking about carbocation. So in general, SN1 and E1 are not useful practically from practical perspective because you usually form a mixture of products and synthetic chemists usually want to get one product exclusively, right? So it doesn't make any sense to use to conduct a reaction that would give you a mixture of products. So now just to recap, first we determine reagent function. Is it nucleophile, is it base, or is it strong nucleophile or weak or strong base, basically. Based on that we have these four categories, and then we analyze the structure of substrate, which can be primary, secondary, and tertiary, and then we combine them in order to make our predictions. And once we find out that these mechanisms, sometimes you have multiple mechanisms competing with each other, once you narrow down from all four possible mechanisms like SN1, E1, SN2, and E2 to some subset of these mechanisms, then you consider stereochemistry and regiochemistry, and we have this table. And we have covered all of these, but let's just quickly recap. For SN2, you don't have any regiochemistry. You have only one position, right? You have only, let's say this, and your nucleophile is going to attack here, alpha position, and your leaving group leaves. So there is no any regiochemistry. But from stereochemistry, you have inversion of configuration. Nucleophile is going to attack from the backside. That's very simple. E2 reaction is the most difficult when it comes to regiochemistry and stereochemistry. There are too many things to consider. For E2, you have a Zaitsev and Hofmann. Zaitsev is the less substitute alkene and Hofmann is more substitute alkene, and that depends on the number of beta positions. If you have multiple beta positions, then you can have Zaitsev and Hofmann, and that depends, and you can control it using a base. If you have sterically hindered base, then your Hofmann product will be favored. Otherwise, Zaitsev is going to be your major product. And then once you determine regiochemical outcomes, for each regioisomer that you form, you can have stereochemistry. This reaction could be stereoselective, where you can form trans and cis at the same time, trans being a dominating one because trans is more stable than the cis. And if you have only one beta hydrogen in one beta position, then that hydrogen should be anti-periplanar. So you have to meet this requirement so that hydrogen and bromine are on the same plane but opposite to each other. And you only form one specific alkene. So this reaction is called stereospecific. So there are a lot of things to consider in E2 reaction, and we have covered all of them when we talked about E2 reactions. And then SN1 reaction. In SN1, because you have formed carbocation, and carbocation is a planar, it has two faces, so you can actually form racemic mixture. Your nucleophile can attack from, let's say, top and to bottom at the same time, or from right and left. It depends on where you position your planar carbocation. But in regiochemistry, since we are talking about SN1 regiochemistry, you will form, let's say, this kind of cation, carbocation, and you can have some kind of rearrangement. that's the only case where you have a substitution reaction would give a different regioisomer, and that's due to you can have hydrazine shift or methyl shift to form more stable carbocation, and you will form a different product. And when it comes to stereochemistry, it usually gives racemic mixture and nearly racemic mixture, because you still have a preference for back attack. Even though you form a planar carbocation, you can have you still have the leaving group in proximity, so it blocks one side and prefers one side over another. And in E1 you have again form carbocation first. Actually, we haven't talked about that specifically, but you can still have Zaitsev and Hofmann product, but Zaitsev is gonna be preferred over Hofmann. And in E1 reaction, you don't have a lot of control over Zaitsev versus Hofmann. And when it comes to stereochemistry, it's stereoselective. You always have trans favored over cis. And this reaction is not stereospecific because you don't have any interperiplanarity requirement, because you are abstracting proton from a carbocation. So you don't have this proton and leaving group being in interperiplanar position requirement. You don't have that. You only have that requirement in E2 reaction, where you have a leaving group leaving and proton is abstracted by base at the same time. This is quick summary. This is for quick reference. All the information here you see is already covered earlier.